My name is Phil James Roxby, and I'm a Distinguished Engineer at Xilinx. This is a technology demonstration of a converged runtime for AMD CPUs and GPUs and Xilinx FPGAs. This converged runtime is based on joint research between the two companies and has now grown into a collaborative project between the advanced development teams of both AMD and Xilinx. With these new capabilities, Xilinx and AMD are unlocking new opportunities in exascale computing, enabling users to more easily take advantage of the best features of AMD Instinct GPU accelerators and Xilinx Alveo accelerators. A user who wants to do part of their compute using AMD CPUs and GPUs and accelerate other parts of their compute using FPGAs today would typically have to deal with two separate software stacks. Stacks like AMD's HIP and ROCm can be used to target x86 CPUs and GPUs, and then a separate stack like the Xilinx Vitis Design Suite and XRT Runtime would be used to target the FPGA fabric and any embedded processors. The user would need to find a way to tie together these different stacks using the host CPU in their application. There isn't a single integrated way to discover resources or to control the work being sent to those resources, and each stack controls its own subset of system memory, making it hard to share data efficiently. What's being showcased today is an integrated ROCm runtime, which can tie together CPUs, GPUs, and FPGA accelerators. This runtime supports a unified way to discover resources in a system, to dispatch work to those resources, and to synchronize that work. The resources use shared virtual memory, which allows buffers on one device to be visible across any of the devices in a system. Users can specify fine-grained spatial data flow compute tasks for the FPGA using synthesizable C code or code written for the AI engines on Versal devices. Then the integrated ROCm runtime deals with the interoperation required between all the resources in the system. Looking to the future, we're working together towards a unified language level and library level integration between tasks running on AMD CPUs and GPUs, as well as FPGAs. The unified ROCm runtime for GPUs and FPGAs has a number of important features which will be demonstrated. Firstly, the runtime provides a unified way to discover and reserve different resources in a system, supporting the scale-out of applications across these resources. Secondly, a unified method of dispatching work to these resources and synchronizing that work across the resources allows users to take advantage of familiar architectural queuing models and peer-to-peer events without having to think about separate methods for separate resources. Finally, shared virtual memory allows buffers on one device to be accessible to any of the devices in a system. So, for example, a GPU can access buffers on an FPGA and vice versa. In order to demonstrate the advantages of this converged runtime, 4 demonstrators have been developed. The first demonstration shows how the converged ROCm runtime can discover CPUs, GPUs, and FPGAs in a consistent way. Running this code on a machine with an AMD CPU, which is equipped with an AMD GPU and a Xilinx Alveo card, will display the names of all of the 3 resources in that system using a common method, without requiring any different code for dealing with the FPGA accelerator. Users can discover and reserve CPU, GPU, and FPGA resources in a standard way. The second demonstration shows how a familiar queuing model can be used to dispatch and synchronize work between an x86 CPU and an FPGA accelerator. Using the system discovery method from the previous demonstrator, a user creates a work queue for carrying HSA packets, which can be written by the CPU and read by the FPGA using unified shared memory. The CPU then enqueues a work packet from user space without intervention of the Linux kernel, and this work packet can contain an event which the FPGA can use to signal that the work has been completed. This is a common method for dispatching and synchronizing work on both GPUs and FPGAs. This demonstration code shows how user-enqueued packets describing work to be done on an FPGA accelerator can contain virtual addresses to reference the input and output arguments used by an accelerator. The use of shared virtual memory enables devices to share complex data structures containing embedded pointers, opening new opportunities for FPGA-based compute acceleration. Shared virtual memory allows CPUs, GPUs, and the FPGA to more easily access shared buffers. In this final demonstration of how GPUs and CPUs can be programmed in an integrated environment, we show an example where both the FPGA accelerator and the GPU accelerator create work queues. The work dispatched to the queues is performed asynchronously. The code shows direct synchronization between the FPGA and the GPU. A barrier packet is enqueued in the GPU work queue, which forces it to wait until the FPGA has completed its accelerator function and made its output buffer visible. This demonstrator shows how a unified runtime can achieve direct synchronization of GPUs and FPGA kernels without requiring the intervention of a CPU node. With these new capabilities, Xilinx and AMD are unlocking new partnership opportunities in exascale computing, combining the best features of AMD Instinct GPU accelerators and Xilinx Alveo accelerators.